So then there's a second thing we all talk about, embodied vision, is this combination of perception and the motor system. We need to offload the cognitive principles. Some of the computations that we maybe over-design in perception can be offloaded to the environment. Dana Ballard has talked much about it. You don't have to store everything. You keep looking again. You look and get what you need. Clearly, biologically, there was a co-design of body and algorithms. Right? So I don't have a general principle on this yet, computational. There have been some robotic sense theories, but I will be showing in the lab, we have been designing systems, drone vision and navigation system, that take such principles and implement them. And I will show a few examples. And then the third thing we learn through interaction, that should be a principle of embodied cognition. And there is adaptive behavior. We adjust our behavior based on real-time feedback and environmental changes. But definitely perception, action have to be coupled, and we learn from perception, we adjust our actions. And in this I will be showing you an effort I'm doing. I'm trying to design a system. In this case, it's not a robot, it's a system that tries to help music students in learning the violin. So you're looking at the students, you're listening to them, and we're trying to tell them, give them feedback, how to adjust their movements in order to get better at the violin. So basically, I will be walking in these next hours through these three topics: the visual navigation research, some examples on minimal vision, and an AI system for motor teaching. This is the event camera. You probably are familiar with it, most of you, if you ever have looked, most of you, at Guillermo's lab, who is the pioneer and has put out all the useful materials, so if you want to get a jump start. The sensor only records changes, and that's inspired by mammalian vision also, that there is a pathway there as it starts already at the retina that only records changes. The sensor is not working like the human vision system exactly. It's actually much higher temporal resolution. And by now there are multiple sensor designs out there, how you do it in hardware. It's the principle. But some of the principles, it has very high temporal resolution and it records in logarithmic intensity space. That means you also can go from day to night. So sometimes we show this, it has a possible visualization is that we just take the events that have happened in a small time interval and we pin them down to make an image. And what that image would be accumulated over 33 milliseconds would be the boundaries that you mostly see, because that's where changes happen. You have a threshold on the change, only when there's a change at the pixel in intensity. So when nothing is moving, you shouldn't see anything. You still will have noise because of static noise, but mostly then just you see the moving things, the moving humans here. And they're encoded whether the intensity increases or decreases. So what we have as output in 3D, you can also visualize it like this. It's the camera, gives you the exact timestamp. So here, I should stay here, I was told, yeah. Let me see the mouse, no, let's see. 1 second, I wanna. Okay, so this is in X, Y, and then the Z-axis goes up. This is in time. So here we've red encoded the most recent. and the blues down the older. So if they hear from this recording, where first the camera moves, we have a lot of events from the background, and then there's an object that's moving, it's spinning on a fish thread. So it's spinning out this motion, and you get this tube of events. So up the axis is the time axis, yeah? Kind of get the idea. So that's a 3D visualization. That's what we're working with. And, well, if you are in computer vision, you know the classic approach is basically to vision is the reconstruction approach, called structure from motion, visual autometry. We're basically looking at the camera, we find exact correspondence, will I talk about, and we're trying to make models of the scene in view. And that approach has been very much developed even before deep learning through robust features made a great breakthrough. And that approach is also on autonomous robots, vehicles. Largely, they're not using vision, but they're also using other sensors like LiDAR, in which case they need multiple LiDARs because each of them has a certain range in which it works. It does work very well, but there are still some challenges with fast changes in system motion. And one of the things, this approach is computationally very expensive. You're taking all the events, you're trying to make a model, you're trying to see how the object moves. And there are challenges with moving objects. So the current technology regarding detection of moving objects is really relying on learning. Object detectors that have been trained on lots of objects, they do work very well, but they don't generalize 100%. So moving object detection, which is actually something you see immediately. If something is moving, you have this detector, you're ducking. If it's going to hit you, right, is replaced by recognition. One thing we have to be aware of, yeah? The classic pipeline, the way we compute when we try to make these models of the world, is as follows. Either you have images for multiple views that you're looking at because you move, you had a stereo system, and what you're doing is you're trying to find points in the scene that you can hold on. In the case of if the views are far apart, and then you try to find the corresponding point in the other image. If they're far apart, the views, like in a stereo system, we compute points. If they're close by, like in motion, we usually consider them, we linearize the problem. We're doing differentiation, and we say the motion in between is a linear motion, and we can represent it in the image by a vector. So on my image, this point moved from here to here with this vector. Yeah? And that's what we call optic flow. That's what the technology is basically, first we try to get that. After we have that, I mean, this comes out here is the problem also explained. We're looking at the world from multiple views. Should have come first. Then after we computed this, we can compute how they were set up. The cameras, what was their geometry, how did they look like, which is rigid transformation, and we're using also inertial sensors can be helped. So IMUs give you very good rotational displacement. And then when we have this, we can also get then back, now if we have the motion and this, we can compute from that the distance to the camera or some kind of a shape model. And in addition, we would like to segment the scene somehow. So that is an issue. And as I mentioned, in current technologies, it is a very strong cue in biology that's done for motion. But in most of current technology, it's done frame by frame via recognition. Yeah, we detect humans and dogs. So one thing I mentioned already, my super slide, well, if you really want to detect independently moving objects and you want to find out how you move and you have to estimate your input, this image flow very accurately, these components are really related to it. Because if you don't know what is the static scene and where the objects, you are hampered in finding out what is the 3D motion. You have to find first those regions. And also to get really good flow is not easy at the boundary of moving objects. So they have been referred to as chicken and egg problems. Somehow they need to be in a biological system really has to worry about addressing all of them in some way. Well, now back to event clades. Our first approach that we had thinking about this was we just do ego motion, estimate how the camera is moving by a very simple model, a simplified model here, 4-parameter model. So this is the scene from Guillermo's thing. The camera is moving on top of this paper and out comes this event stream. Yeah? And what we did then in this thing, we take this event stream and we bin it. That was a number of years ago. And within each bin, a small bin here between time t0 and time t1, we say, let us assume the camera moved. I can model the motion of the camera. It is not going to change. So if I know the motion of the camera, I'm using a simplified model, then I can tell you at each point how each point moves. Yeah? Apply that. And then move each point counterwise. So I take that whole slice of points and I move it to time t0. Each point has a timestamp. And I move it, I multiply it just with that time interval that it moved. And if I moved correctly, they should align. So I warp them back. And this is the work that Guillermo has been very famous for. It's called, he had various formulations on how are we going to actually solve that. And the way he solved it was he took the intensity images. So here are the events in number A. And if you take all these events and you plop them down to an image, they become blurred. And if you can align them, you estimate that motion model, then you should get sharp edges. Now, how do you optimize for sharpness? Because you have to estimate the parameters that give you sharpness. That you can do in various ways. You can estimate the variance. And what we did this kind of in parallel. We were working then on the timestamps. So we didn't use in our first work the intensities, but we used the timestamps, which you see here on the right. And the advantage of the timestamps is that kind of the gradient of the timestamps goes in the direction of the flow. So with 2 iterations, you basically have aligned because you can just move in that gradient direction. And that was our first work, and that was a very, so basically that's what you do. You try to warp the event, you down projected it to the image, and then we compute the gradients on that image, and then in 2-3 steps, we are there. And the advantage was, well, it was running very fast, even then, in 40 frames per second on a single core. The CUDA implementation there, but the first work wasn't really doing ego motion. It was doing a simplified ego motion model. Basically, when you take this down, it assumes the depth is constant. All right, so here are some results. So what you will be seeing the way it can be demonstrated is strobe light, which the camera provides. It goes from dark to light. So we have here various objects. They're behind the net. and they will be moving around very fast, and we detect the independently moving object with that rather simple algorithm through the square that you can see, and you see many different scenes. It was successful. In order, then we started realizing motion segmentation, ego motion are very good problems for this sensor. This is what it's good for, because it is a motion camera. It gives us good motion, at the boundaries especially. And we invested in collecting some data sets for independently moving objects in the lab that are called right now EVIMO, in event independently moving objects, and then event independently moving objects too. So the first one had a camera that comes out from Zurich, both intense, that actually records intensity images and events on the same camera, two independent components, but at lower resolution. And then the second data set, we built a stereo rig and put the cameras we had at the time, which was a Samsung. They had given us the early prototypes. They didn't pursue it. Unfortunately, Prophecy, which is the main camera, was on it. And then there's some regular cameras on it. And the way it was done is that we have a Vicon system. So the objects were scanned, high resolution scanned, so we know their geometry exactly. And then we have trackers on them. And as we record now, we know exactly how they are moving. And since we know their shape, because we scanned them beforehand, we know now exactly where the object is and where everything is. So automatically then the motion can be generated and the masks can be generated where the object is. And that's what the data set is providing. And in this version now put out will also provide the optic flow for evaluations, so people work with that. Well, now a little bit going more into biology. So if you're not into computer vision, you may even say, what the hell is she talking about? Well, I have been talking about this optic flow input. So this optic flow input is these little vectors that tell me how is every point moving, every scene point moving on my image from in between the recordings, yeah, in a regular camera. So that's what is called optic flow, and you see here the vectors displayed on this image. And often, if you look at the paper, often the way we display it, we do it color encoded. So we show on this color disk, yeah, so with the color then being the direction, and then the intensity being how long the vector is, yeah, some encoding. But the issue is, in order to get good optic flow, the processes that are done are not cheap. This doesn't come out two-dimensional very easy. And actually, the computations behind are very expensive by now, what people are doing. Locally, what we're talking about is that when we look at an image, if we just want to look locally, because we cannot look all over the image, locally we can make the assumption there's some movement. At the next further away, the movement is very different, right? So locally we can say, okay, there's a constant movement, but locally usually we have edges. Some kind of, the texture usually only gives information along one direction. So we call this the aperture problem, meaning I'm looking locally, yeah, at a local part of the image. I can't really say what is the flow. Is it here or is it here? If I have only an edge in the image, I can only say the edge moved this way. That's physics, yeah, it has nothing to do with how I do it. And that component, while this is a 2D component, so locally I am only confident about this 1D component. which, because it's normal to the edge, it went into the literature being called normal flow. And here you see the Barber ball illusion, which is an example that shows the normal flow where the system, there's nothing there, there's just the edges. So also the, you know, in the Barber ball, it's actually, the movement is actually going up and down. Yeah, the thing is rotating, right? The Barber ball is rotating. But you don't see it rotating when it rotates. You actually see some upward movement or downward movement. And this is exactly the reason, because you can only compute the component along the edge. And then what the system does, it matches things at the boundary, at the edge boundary of the Barber ball, and fills in from there. And this happens to be false. So this is a nice example of normal flow. It's there. Well, in an image, what it would mean here, whatever the drone takes here with its downward facing camera, it's going down. So when it goes down, everything would be expanding, and the flow would be something like the blue thing, but then the normal flow would be only in one direction, on some direction, where the edge is. Geometrically, we can interpret it as the projection on that direction, whatever it is, which is defined by the texture. But we just can compute that from images via different methods, how they change from their changes in space and time. And filters are applied, Gabor filters biologically modeled. Like Adelson-Bergen, he proposed a model here where he says we have Gabor filters in space that are tuned to certain directions, and then they also can be tracked in time. Now we're checking them in time. Yeah. And that can give you reliably normal flow. Even what you know, simpler models like the fly vision, which is modeled by a Reichert detector, just a correlator. You just say, measure different displacements, you have set them up, and then the maximum displacement that it responds to is tuned. That could estimate a 1D component, but not a 2D component. So biological systems, if they are simple like flies, they're not likely going to compute flow, but something that's simpler and local. And why not flow the way we are having it? Because it requires you to take this local component as the first constraint, and then you have the edges, at the boundary of things, there's discontinuities. So you need to make a second assumption. Usually we make the assumption that it's about the same in a neighborhood. It's changing smoothly. But then you need to take care of the boundaries. So you have to introduce additional constraints there, that it follows the boundary, that we can detect occlusions. All these are in optic flow algorithms in various ways embedded, and they optimize over the whole image frame. But A, that's not cheap. B, it doesn't absolutely work at the boundary. So it's not really, even with lots of work, it's not absolutely reliable. So, since I said the principle, let it be simple, what can we do? We can do, and let us do this in event space. We have done normal flow before in vision space. What is it in event space? Ben Osman wrote the first paper. Basically, when you have these events that are coming out and they are making these 3D space-time things, if you look at the tangent plane, you only can say that the normal flow lies in the tangent plane. And he wrote the first algorithm, he fit the tangent plane to it locally to a 3x3 events. And that built then on top actually a flow algorithm, but that is locally just 3x3 events throwing out. It's not accurate. Nobody can build anything on top of that that would competitive. We also need to be competitive. Also the neuromorphic community may say we implement it on spiking networks. Yeah, okay. We are in vision. We want to be competitive too, yeah? So far. So what we did recently, and excited to report just the newspaper coming out by the Hao Yuan, we developed some robust descriptor. When we work with these events, first thing we gotta describe these clouds locally. And the way we describe clouds now is we have a local point cloud, which is really based on density estimation. And we describe each event now, the neighborhood of each event, at each event with a vector. And then we do, this is now our descriptor. And then we use that descriptor, which has information about the whole events, to train small networks, like here a small network for normal flow. So to give you the intuition of this new encoder, by the way, it's now implemented in CUDA also in real time. So now we can build things on top of it. When you have these point clouds, the work started already for originally thinking about point clouds, not event clouds. You want to represent them, whether they be sparse, whether they be dense, whether they be mixed. You want to have a representation for them via some feature vector. And there is something, if you describe your object, in this case the point clouds, via a density estimation. So you fit a probability distribution and you do density estimation, which means you approximate your discrete points, your discrete probability, with kernels. You get a smooth approximation of it. And if you use the Gaussian kernel, the radial basis function, there is a theorem that says you can represent it via so-called random Fourier features, which means Fourier, take the Fourier coefficients of the whole thing and just apply a random matrix applied to it and select those, and they can represent it via your Gaussian kernel function. Yeah, so basically what it says then, this local geometry can be computed via exponentials times a random times some random matrix. But you can also implement this efficiently actually if you take the whole event slice, so you take the events within a certain amount of time, usually takes 33 milliseconds, compute the Fourier features, compute the Fourier coefficients on it. And then for each, so in parallel, for each point, then pick within the neighborhood, where the neighborhood can be encoded as kernel size. So each point encodes, are you a neighbor or not? So are you in a radius of 10, or are you a certain radius? And then pick the random Fourier features and compute it like that in parallel. And then I went through one more iteration via CUDA implementation to actually take away the adjacency matrix and implement that also as via convolution. And, yeah, so now it's real time and available. And code is available, both implementations there. So what it does then do as a sanity check, if these are your points on top in some events, it fits this gray, these kernels to it. That would be an approximation to it. And that is then represented by a vector. So now you have a vector representation you can work with. And the first thing we did is go back to normal flow fit. So take these vectors and we train the small network, multi-layer perceptron, to just output normal flow. So we have that data set that I showed you before, the AVIMO. And there's also other data sets available, which we also used. And we just said, what is normal flow? So normal flow basically means that the normal, the flow is the normal flow, and is the projection of the flow. So if I subtract from the flow the normal flow, it has to be perpendicular to the normal flow. Yeah, the normal flow can be anything. It's just the direction that comes out somehow. So this you can encode here. Basically, you enforce the radial component. We say the normal flow minus the half the flow normalized should be basically of length 1. So if I take the logarithm, it should be 0, and that's 1 in the cost function. So you enforce the radial function, that's how he did. And the second component, since this could collapse to 0, he also enforces it should be as close as possible to the optic flow. Yeah, if there is information there, make it as close as possible. And that's how the network is trained to spit out normal flow. So what it spits out is a 1D component. Sometimes it's flow, sometimes it's normal flow, but you don't know. It's just a 1D component for you, and it gives you what the direction is. And here we see, sometimes it's flow, sometimes if there is, like in this neighborhood here, where there is actually a whole cloud of multiple directions, it actually predicts flow. But for me, it's still what it outputs, it's normal flow, and then we also output. We can also output the confidence value of it. But now I have something good to work with, and I can work with it. We also tried, we can use it now as a universal descriptor. We also tried flow estimation, but it cannot learn flow so well because flow is a very global concept. You have to look all over the image. You don't get this from the local neighborhood. That's what optic flow algorithms do. So normal flow is the local thing to do. And this here just shows you some experiments. When we compare it against some data set, we're doing about equally well. When we compare it on our data set, which is really EVIMO2 that has boundaries, it does better than other algorithms. And current algorithms can be model-based, like work here. They can be learned supervised, they can be self-supervised. And you can train them on a few data sets and apply them to multiple data sets. So here are some examples. What it does, and I wasn't expecting that, it gets the values so well at the boundaries. I always thought at the boundaries you really have to go in with flow, but no, it does get them well. Yeah? So what can we do with it now? We have these normal flow values. We can actually do many things, but in the domain of 3D motion, we can definitely solve the ego motion. And well, classically, when we have the flow, our flow estimates, what it does is what we're going back is basically an equation. We're saying, so if I'm only moving, then all the changes in the world, nobody else is moving, can be explained by my own motion, which is 6 parameters, my translation, my rotation. And this can be explained, the translation, so a vector, 3-dimensional vector v, but it also depends on the depths. How far is each point? So points that are further away move little, points that are close by will move big on the image plane. And some matrix A that is given. And then the rotation, which doesn't depend on the depths. So when we have the flow, the way the literature has worked, they can solve it. It's called the epipolar constraint. And the idea is basically you take the flow, you subtract that rotational component because that doesn't depend on depths, and then you're left with something. And that something should be parallel to the translation. So you minimize the error to the rotation. And in principle, there has been lots of work before on video. In principle, since we have 2 constraints from each point, we can do this with 5 points, non-linearly. And classically, we linearize the problem in a way so that we can get 8 vectors via linear algebra. And then out of those 8 vectors, we go back and we decompose them to get our 5. It's actually just 5 because if it's one camera, you can never get the depths. That needs to be coming from something else, like your IMU or your integrate or your acceleration. However, if you have normal flow, you don't have this luxury. You only have one measurement, and each measurement has its own depths. So over the years, we have been thinking, long ago, we solved this problem already. I introduced pattern, but for intuition, the easiest way to think about it is if you only had translation, let us say there's no rotation. So that translation, the normal flow measurement is really the translation over the depths. And then we multiplied, it's projected on some direction. So if I only have the normal flow measurement, all I can say, it must something projected on it, yeah? So that angle between has to be smaller than 90 degrees. So the flow could have been anywhere on this half plane, coming anywhere from here to here, which means if I look at, it could not have been the other way around, because that would have given a projection in the other direction. That's all I can say if I do not make any assumptions about the scene, which means if this is the translation that there's a point in the image plane, a translational flow field from which everything emanates has to be on the other side. And we solved this in early days. Bertolt Horn already introduced linear programming, or we geometrically by taking these half planes, intersecting them geometrically, or now they have implemented the support vector classifier. A few years ago, we applied some optimization techniques to the whole flow. So we said, this is the optic flow. So the normal flow is the projection of that flow, yeah, on a gradient direction. So if we do not make any assumptions, all we can just say, if we know the rotation, so take the flow minus the rotation, then it should be still parallel to the translation, which means the translation and this derotated flow, the scalar product, should be greater than 0. That's all you can say. That's what you can minimize, but that's an inequality. Hard to optimize. So what we introduced is then we say, we're not rating it as, is it greater 0 or is it smaller 0, but let us put a function on top. And that function being the ReLU function or a smooth version of it, like the GeLU function. So if the depth is then positive, we're not punishing it. And if it's negative, we punish it proportionally to its value. So now we have a smooth function that we can optimize, and we solved it with optimization packages like interior methods. And then Barranco did that, and more recently than Chetan implemented it in a deep learning network. But it's now something differentiable, yeah, which before it wasn't. Okay, so in this case, what we did now, there's one more thing. Early on, I proved already, yeah, you can solve actually ego motion also via proofs from normal flow. So it can be solved. It's not that it looked at how does the optimization behave. So it can definitely be solved. So what we did here in some implementation for the usefulness of normal flow, we do a VIO application where the rotation comes from the IMU, and we estimate the translation via a vector, support vector classifier. And you see here just this very constraint, which is rather weak, because all you say the scene has to be in front of me, lets you estimate here the path of the translation very well. The red and the blue fitting. You see the line, okay? And recent work, I said problems have to be solved together, and here's a very first approach, not even put out yet, but they have to be solved somehow together. And the approach is then kind of iteratively. Let me first estimate let me first estimate the ego motion model, a simplified ego motion model, which, however, can be good enough to at least find the regions, some regions, most of the regions that move independently, as a very first step. And then when I have this the background, I can do some ego motion estimation, like translation estimation I showed you on top. And then, so what we did then is, but you can't rely on this perfectly. Now, having this good normal flow, we can estimate it and we can do some hierarchical clustering, what we did here. And it works actually very cheap clustering, just what is same as a starting point, which is real time. And now using our background model estimated here, we build it up over multiple frames. But the background model allows you now to align the background, from which you then can get a background merging. So we start merging, now having background and foreground. That's the background merging, but with kind of ego motion estimate. And then we track basically the foreground now by hierarchical clustering this and fitting motion models to neighboring points to get them very accurately. So here you see some results. That is what the normal flow algorithm will give you. See here. Oh, that is the results on the right and the input of the normal flow on the left. So now the first version is ready, only on motion. So to summarize what I said is that we have now a powerful descriptor. We used it here for normal flow. For a real-time implementation that I believe opens the doors now for robotics in event vision, because now we have something real-time where you can build your segmentation on top, you can stick it in your control. But even the descriptor before it is done as a normal flow, you can use for other things, for recognition, boundaries, things you can build, other small networks on top. Yep, okay. Well, some other work I will not bother you in the next section. You will just see videos. We talked about the second principles. Equations are over for my passion. For embodied cognition means combining vision and perception and action. And classically this, I mentioned it already, we're doing all this work, reconstructing the world, triangulating. That's what that current technology does. And it is working in applications, but it's not biological. It underlies anything from autonomous driving, drones, also augmented reality, virtual reality. All this technology relies on structure for motion and SLAM. But biological systems still do it. They do it cheaply. They don't, not reconstructing. So by this inspiration, some systems were built, like just enjoy now the next videos. Here's a system that just wants to land. So a DBS system. So if I want to land or avoid or detect drones, all I have to do is detect those moving parts of the drone as an idea, and I can guide already some control. So that rotates very fast. The blades rotate very fast. And the event vision can see those fast movements. It's not blurry for event vision. So now you can use this technology. For example, here you see what you compute on the right to detect drones, to follow unmarked drones. Or you can also use this a little drone now that lands on the big drone in between the blades. Very simple, doesn't compute anything, doesn't compute what the geometry of the world is, what exact depth is. All it does is compute this landing thing. Yeah? simple Q. Or here some other work that recently was done by Nitin Sanket and Chahat Singh. They trained a network to detect uncertainty, so like the variance in flow. Well, they do it in a, they train supervised on the flow and then self-supervised on the variance. So the network will spit you out the uncertainty of the flow. And then they just used, each pixel now has an uncertainty, this uncertainty in various tasks, like when you have want to do dodging. All you need to do is you see things coming, which ones are closer have higher uncertainty in your map because the flow is larger. Or you want to go through a forest, at the boundaries of objects you have high uncertainty. Or going through a gap, the gap has high uncertainty when you have a large displacement to it. Or segmentation, when you want to pick something up or segment a heap, the things that are closer have higher uncertainty. And the next video basically shows the navigation through this indoor forest, what the drone would see then. It's like, I mean, this is the forest in the lab, the tubes. So the map that you see in on the bottom is the uncertainty map colored, and it only has to see where it's uncertain to see the tubes. Or here a dodging example, where it sees the close by objects with high uncertainty, because the flow is larger, so the uncertainty is larger. And here a new example from the work of Levi Berner about embodied cognition. And the idea is basically, so we live in a world, we interact with objects, and they have a certain distance to us. But if you ask me, I cannot say that that chair or that object is 1.5 meters away. I wouldn't know that. I kind of know it, and I know how to interact with it. So I more know the distance in my embodied space, how I move to it and how long it will take me, what it means in terms of my own movement. Yeah, instead of knowing exact depth. What is this distance really? However, robots, the way we design our robots today is we recalibrate the vision system, we put the stereo on, we spend time on recalibrating it, whatever it is, or LiDAR. And if we want to, for example, go through a door, the designer of the system needs to know exactly how large the door is, measure the door, enter that in terms. The system can then estimate from its stereo or LiDAR its steps, and it knows how large the door is, pre-calibrated, and then being totally calibrated, and then figure out whether it fits through and how to go there. But animals, coming back, animals do that. They probably do not. They don't have exact calibration. And the dog can learn how to do these things somehow in terms of its own motor movement, or other things too, like the hummingbird. It flies and can very accurately go to these flowers, begin probably not estimating exact meters or centimeters how far it is. As mentioned, the way the current sense plan architecture works is that we have our state estimation, the perception system that works in meters. Then we need to plan, giving this in meters. And then we have a plant, whatever it is, our voltage, yeah, that we're giving to it. And somehow we need to go from these meters to the voltage that we need to apply, which means the system needs to be accurately calibrated to get from here to there, right? And our controller will then knowing exactly what it means to move or to lift, translate these meters into the embodied units that you need the voltage or so to apply. But that requires accurate calibration. So what Levi now instead imposed, we are not estimating accurate distance with our sensors. Instead, our controller computes embodied units. And our vision system computes embodied units. And then the planner gets embodied units. So the controller can do its work. And the trick lies really that this embodiment, which we can say is the accurate estimation, the x hat, divided by this embodiment, it turns out this drops out. So the factor, the control factor B and the vision factor B can be divided through, so nobody has to compute it. It remains embodied. Intuitively, in the vision space, what it means, for example, that we are not computing the distance xt, but assume the current distance over the distance at time d0, which means, for example, the change. How much is it changing? The time to contact. Or if you compute the trajectory in structure for motion in VIO, you have the trajectory divided by the scaling factor. So that's what we're going to compute, this embodied vision community. And the way it is done then, that we can say this phi times x0 is xt, or our phi times x0 is, when we take the body in, it's x0 plus developing it times t x0 prime plus the second integral over the acceleration. And all this, the vision is embodied, the x0 is in embodied units, so divided by scale. And so is the derivative and the second order.
What do you mean embodied units?
I don't know the exact calibration. It's up to a scaling factor.
Oh, okay.
Up to a scaling factor, you may see it in terms of the vision. Yeah? Mm-hmm. And the control also works up to that scaling factor. Well, and with that, Levi implemented uncalibrated touching, uncalibrated clearing, and uncalibrated jumping. So what the system does, it moves in front of the, like you will see in the video, it moves in front of the clearing to build up as it moves and integrates over its acceleration and velocity, to build up these terms in terms of its movements. As you see in this video. Okay, that's something. So the robot moves in front of this object. As it moves, it integrates. It computes the looming, how the object changes, so the size of the object, divided by the unknown scaling factor, and the same on the control. Or it moves sideways to see how large the object is in terms of its own size, comparing it. Or it moves closer to the object. In order to pass through them. Well, I think, so I have spent now an hour. We can spend the next half an hour discussing. Or I can spend another 5-10 minutes on showing you about another project. Lots of questions, or you want to hear a little bit about violin learning?
So earlier you talked about like the normal flow and how that's a local flow. I did not quite get how you get from like all of these local normal flows at each point to a global optical flow.
I'm not estimating optical flow. If one wanted to go from normal flow to flow, but that's not what I'm doing, then you need to go back to the classic assumption. You say the normal flow basically says something about the intensity remains constant. Then you need to make assumptions about the scene is changing smoothly. I'm trying to, at the same time, so I'm applying a regularization term over my whole image. At the same time, I'm trying to find the boundary of moving objects. So I'm applying 1D constraints. I'm trying to follow that and detect the occlusions. But that's exactly what I'm not doing. I say I'm only going to work with normal flow. And what I showed you was we can do ego motion that we know for a long time. It's a weaker constraint, but we can do, and most recent, which I wasn't even, I didn't even think it would work because it's doing so well at the boundaries. We can even do motion segmentation with normal flow only. Yeah, I was always thinking I have to go back to flow and the line, the alignment constraint, but we actually can do it with normal flow.
But this will probably depend on the motion. The motion that you show for the motion segmentation was lateral, mostly.
You know, the normal flow really comes out well. The normal flow is very well estimated at the boundaries. Do I now, the whole segmentation problem, estimating segmentation and ego motion, I showed you our first approach, which is now so on GitHub. I think it needs a bit more if objects are really large in the scene in view, but there's other things we can use. But even from normal flow, I'm sticking to my normal flow theory, or at least my vector theory, right? I think we can do it locally. Sometimes we're even fooled with independently moving objects. If you're sitting in a train, everybody knows this experience, and you're looking out, the train starts moving, right? You actually think the others are moving. The world is moving. You can't decide on the basis of this information only. Yeah, then you need to look somewhere else, maybe to the other side, and figure it out.
Would the normal flow work well also in the forward motion?
It does work well locally. It works locally on the edge, yeah? It does work locally well. These moving objects, some of them really move very heavy. They have very, it does get it very well. The current CUDA implementation loses a little bit accuracy for real-time clustering.
Yeah, I thought I'd just moderate the question so that you don't
Yes,
have to
very
keep track
good.
of
Yeah,
people.
yeah.
There was a question first about the
so for some tasks, event data is not enough. So you need like you just need like the normal intensity image, but you can also reconstruct that out of event data, which is something we are doing right now in the event vision lecture. But do you think, like my question is, are you competing with like cameras that put out intensity frames, or do you see it more as event vision being like an augment, like
Second one, I really see augmentation, yeah. And even you do both, right? We do have what comes out of our retina is doing a lot of pre-processing already and compression. And at the end, we do both work with intensities that mostly go to the recognition and the events that can be doing a lot of the motion processing. So for this structure for motion problems, what we call structure for motion navigation, the big difference to anything recognition is you don't need to recognize anything. This is just on the basis of geometry. We relate how, as we move, we can relate through equations how the image changes if the scene has a certain depth and the motion is a certain thing. But I do not need to recognize that I'm looking at a chair or at the door. What I'm getting is this information, this motion information, navigation information is pure geometry. It's how far things, or I may do many things with relative depths, because there's no need to get it in order to get things done. We can get the 3D motion. We can, of course, add in other sensors to make our life easier. The IMUs are easy to use, so use them definitely. But there's no processes of recognition or remembering necessary. That's the important thing. When you go already to a task, like even action understanding, I can only recognize the action because I have done it, experienced, and the more I'm familiar with it, the better I recognize it, right? If I play tennis, I will look very differently at it than if I don't do it. For that, we think you remember definitely also in image space. We build up memories, very different. And the current thing, I think you should use both. Also, the technology is now developing. There are already sensors that have a combination out of it. Next research, even for action understanding. I mean, for static images, it doesn't, the event sensor is not helping me very much. Also, I can reconstruct, right, at high resolution. But it's for dynamic scenes. We should figure out now, which people haven't touched yet, where event vision, even in action understanding, does give us an advantage over video vision. I did one paper with Francisco Barranco where we looked at some specific actions. Most of the actions that the community has been looking at is too, they're very different. I'm looking at, am I running versus standing or walking? I mean, you can see this from 2-3 frames. You don't need the video. Or if a very popular action understanding is this manipulation data sets, you are in the kitchen domain now. They're egocentric, the whole community, not the whole, many people that are interested went together and they were in the online cameras and see it from their own perspective. The ego motion data set, and they have lots of actions, but you do understand the cooking actions, for example, which are a large part of them. You understand somebody has an egg and a pan, and you know already it's gonna make eggs, right? A few frames tell you the story, right? If you really wanna break it down, I have been working a lot on this action understanding too. Our philosophy always, we need to break it down, right? We need to break it down at essential things, when things come in contact, if I want to understand the manipulation, not just run a classification. But in actions, what I want to say, we did some things that are very similar, fine-grained actions, like for example, we recorded a data set where people take an object like a glass, and then record different actions. So the glass is there. Well, now it's behind the thing. All right, so I'm grabbing the glass and then I can either drink from it, or I can throw it, or I can hit with it. But I got inspiration from psychology. As you're approaching the glass, you prepare your fingers already a little bit different, whether I'm going to throw it at you or I'm going to drink it from you. So what we did then, recorded with both video and DVS and looked at the differences. In this case, just running an ordinary transformer. It gives me advantages, the DVS, because it doesn't get confused. It doesn't actually see the object before it's touched. But we had a rather small data set, so, well, maybe if you recorded more data, the transformer would eventually pick up the right thing too. So, and you want efficient architectures, but I really think we need to go, one research avenue could be really, for example, in action and the thing. Where does DVS give us advantages? And we need to break down the actions. I mean, what's happening in the community, I show it's mostly you give predefined videos and then people run their classifiers on top. Well, the real problem is you have your cameras out and it sees all the time, and it's your job to chop it up into little pieces and interpret those pieces in order to make sense. Then generalization will happen.
So would you say that event cameras are, I mean, you don't need video cameras anymore?
No, I say let's figure it out. Next step, let's figure out where event vision helps us. And I gave you one little thing, what I call fine-grained actions. I demonstrated with Francisco. We have an advantage. We are faster. We can recognize it faster because somehow the motion in the events picks up how you probably prepare your fingers better than just the video. But let's look at action understanding and see where it helps us.
Yeah.
But yeah. There's definitely a recognition component inside, right? You're not going to understand what it means to cook an egg unless you have seen it before or done it before. Yeah, you need to know all the ingredients. So it's not just geometry.
Was there a question?
So from a more hardware perspective, as we can see here from Levi, I think you worked on this. There's a lot of interaction happening. Is there also work going on to make sure that the drones or the car are robust enough to handle these experimental interactions?
Well, I mean, you mean we use the existing hardware, but that's exactly the point, that you don't need to calibrate even the control. Levi is a control person. You don't need to calibrate exactly for weight, even the robot, right? Or even he had some other demonstrations where he used the track and then he loaded up the track with weight and the track had to go through, but without the calibration of this, because it's learning in terms of its movements, distances, it can do the job.
Then it's learning the way it does decide how to learn or approach something to figure out how fast it is or how heavy it is in relative to...
Right, by just whatever, integrating the looming effect and integrating its acceleration.
How does it choose what action to take to learn or to...
Well, that is when we build a big system. Right now we're yes, of course, then you need a reason on top. Yeah, for the moment it's, yeah, I mean, well, obviously then the system has 100 capabilities, then it needs to start understanding the world and needs to reason, now I'm going to measure
I just thought
the door, yeah.
that what you used for the drones to dodge, for example, where you had the uncertainty, that would sort of be something where things that are highly uncertain, you might not want to test his relation to the world on those, right? So you would choose objects that have low uncertainty, right? And orient himself based on that.
Yes. I mean, basically, high uncertainty, large flow, high uncertainty also. Yeah, I mean, there is a correlation. You probably could do something from flow directly. Here it was the demonstration, but you can do more.
Thank you.
Yeah.
Okay, freedom.
I had two questions. One was, you showed this video of the markerless kind of or like estimation where one drone landed on the other. Which principle does this rely on?
So this was just a vision principle. It just detected, it knew it is a large drone with multiple rotors and it needs to land in between. So just explaining, it detects only the rotors. It's trained to detect the rotors. And
So it's data driven, or
yes, it is a network that was training. Yeah, it probably can just, yeah, it was trained.
how does it differ from using frames in that sense, or it works because we have?
I
small
wouldn't say
time frames?
it was not programmed on normal flow yet. This is a little bit older work, more motivational. It was not using the normal flow, I admit. The normal flow is the very recent work in the lab. The videos are from older times where we also computed.
My question was, it works well because we have a clear image of the rotors because we use a very small.
Yes,
event
yes,
time.
yes. It is done via exactly this, yeah, time slices.
And then my second question was, will there be more sequences of EVIMO too?
Yes.
Because I heard that at some point.
Yes,
It's a
Lieber.
really
Yes,
cool, very
yes,
useful
we
data set.
wanted to do it. Yes, we need to do. I know it's really lacking. There's the real issue if you really want to do ego motion estimation and independently moving objects, we don't have yet very good scenes, right? Yeah, I know that, and yeah, going back with new people. Start from scratch over, yeah? That's the problem. Yeah, no, yeah, we need to do that. And we wanted to detect humans too. It's in the planning for a while.
Could you play the video again of these uncalibrated examples? Because on the slide you have this acceleration is b times the sine of t. So I mean, how could we, without knowing what's going on, interpret this as if not that you're using the first couple of turns back and forth to calibrate the system? How?
But I'm not estimating depths. It's just estimating this x over b.
Do you command the robot to move so much
No, it can move anywhere. It can move anywhere. I mean, it knows how much it moves, yeah?
How does it know?
No, it knows. I mean, it doesn't know. It knows only its acceleration, and it integrates over its acceleration. So it finds its scaled velocity. Its acceleration, it knows. Yeah, that's the only thing integrated over, for which it gets the scaled velocity and scaled depths.
So it relies on an
So
accurate.
basically, it integrates our acceleration together with the vision, yeah, assuming, in the implementation, assuming frontal-parallel plane. So it's actually the Lucas-Canade algorithm, the expansion. And out of that, integrating sufficiently long enough, it computes scale velocity and scale depths.
We have 4 questions. Maybe we could see the violin project.
Well, good. So violin is my collaboration with Irina Morozano. You can hear online, she's an excellent performer. And what we're trying to do now, because Irina got bored over COVID, and it became very hard for music teachers, that was her motivation, to then teach. They did the online teaching all over Zoom that came up, right? We realized there's a need there to assist violin players in their practice. Kids, they grow up, and so what are we doing? we want to create an application to assist violin students eventually of all levels, but as we are doing, we're adding in gradually more capabilities for feedback. So we start with pose, we're working now on posture, we also have a rhythmic band where we help them in teaching rhythm. And quality of tone production. We also want to help with curriculum assignment automatically, so students will get evaluated on how they're playing. And then Irina has been, to do that, we have been recording all the little pieces that violin students have to learn, which are called etudes, and they will be now all professionally recorded. To help on the basis of now you know how the expert plays it, how to get there. Well, I see it is useful because also from a humanity point of view, and that's why the university actually likes us a lot. The music department is doing now AI, because there is a demand for online education. It reduces the cost of learning. I mean, if the app, when it's working already partly, it can be used by anyone, by any online students in Africa, minorities. Learning an instrument, especially the violin, is done mostly through private education. And in America, that's very expensive. They are not public schools. It can also help the teachers. I mean, they want to know what the students are doing. And the parents want to know. Actually, in America, the way violin teaching is done is through the Suzuki method. As I discovered through interviews, half the students still learn the Suzuki method, which is by feeling, which was invented in Japan many years ago, but the Japanese wives were staying at home, so the way the teacher actually goes before you get on the student, the mom or the caretaker has to learn the violin to some degrees. Most mothers don't have the time anymore, right, to learn all this violin, but they need to do this. So a system can help. It is interesting coming back to our inspired, embodied cognition, because we are relating sound to physical action. There's obviously the way I am moving, that's the way the sound comes out. So I can study that. And it's also from a technology point of view, we're teaching a motor learning task, so how do we do that? Most things are not motor learning tasks, right? The algebra and English, that's what we can teach, but how do we teach a motor learning task? And to that end, we will be recording, not me, but Irina recording the etudes, and on which we can then also easily, hopefully, evaluate the students' skills. So first skill is pose analysis. Students will struggle, if anybody playing the violin, struggle a long time doing the pose correctly. This is not done in a year, this is done 5 years. You will still make mistakes. So, correct posture, are you shifted to a foot, some example, are you holding your arm too high, too low? Violin is string instruments are very difficult to play. So here a student that's playing and whatever, for example, too much hip. So how do we get there to these first things? What we did, we recorded data of violin players with our Vicon system, well calibrated. For many views, in the original one, when we recorded it, started this effort a few years ago, we were using the special software. There is a motion capture system, but it had markers on it, so you have to work. And we let the students play a protocol. certain strokes, scales, and then pieces that they play. And we had all this recording. We put markers on their fingers, there are the markers on the suits, there's the sound recording from cameras to have a first data set just to work with. And what did we do with that? To just train a pose estimator to come out well. If you have ever worked with it, there's obviously good pose estimation and it's getting better. But it doesn't capture completely the violin, the delicate movements that you're doing with your hands. So the first thing was a long effort to combine vision and audio to make that pose estimation specifically better for the violin estimation. And it was a transformer architecture, but a hierarchical transformer architecture. And it was trained in both with posture, velocity, and acceleration in the movement to get there. So this here some example of an expert violin performance. And it now has pretty well already defined movements of the hand, the small movements, yeah? Okay, now you can, if you have this, of course, you can give feedback now to the student. That's the idea. Here are some examples. Because it was combined, I mean, the idea is because the motion causes the sound, there's a causal relationship that can be exploited. Here's some shown how our ground truth does better on these very fine movements of the hands and on the bowing motion. And this is now in this first system where then a student can watch himself and gives him live also feedback, like raise your violin. Some other things, and that's basically I will be stopping here, is now, which I think is interesting. Now, how do you teach bowing? There's 16 bowing techniques that a student has to learn. Détaché, spiccato, riccatto. So what we did then is working on annotated data, again, many recordings. We segment the pieces where there are certain places of that you play a little style. So détaché, martelé, so it depends on how you move over. You know violin? You look so, yeah? Yeah, okay. So for this, for you is familiar. Sautilé, whether you move smooth, whether you start with a very fast movement, the motion that you're applying on the bow can be broken down into phases. You have an attack in the first phase, then the movement, then the release, and then the transitions. And depending on how you do this, with what velocity, it gives the different stroke pieces. And that's what you need to give feedback here on this. So, well, that girl doesn't play too well, but that's reality for the beginner. Sound is not coming out, which may be nice for you. Okay. All right, okay. She's playing, she gets feedback, and then after the feedback, she actually learns more attack acceleration. And this is kind of work that is going on now. How do we want to learn actually now? By giving feedback on how do you get better on bowing techniques. It's not a trivial thing anymore, very fine motion. So the way we are working on it, the violin student is playing, and out of this we have now the technology. We can estimate his bows. We also have many audio models that give us audio features. And now we would like to take his current playing, his bows, and listen to him and tell him, you gotta change this to get better, or to get to a better level. So the way we're working on it is that we have this expert audios to which we know this how it sounds and this how it should be done. And to this one, we can relate it now to the movements. There's a rich literature that tells you how violin movements on the string relate to sound. So a physics-based modeling, and we are using here a neural operator that allows also for lots of noises to go from sound to motion, to have a basic starting point. Now, having this embedding, we will be as it goes on, we're doing reinforcement learning now from the student to the state. How do you change now your movement in that state space that you have in the audio and motion space to get from here to there? To get then the output in motion space, how do you adjust your motion space? So here a real embedded relationship between perception and motor. And then to make it useful for the students, we will be also engineering large language models to tell them feedback. And here goes the thanks. Obviously, there's lots of people involved in what I told you about, and that's the How and Howard and Anton who created the data set, and then Levi, Nitin, and Jahad who did the robotics, and Snehesh and Seong who were doing the violin. We call it violin. AI. Violin. Okay, maybe it's out in a few years and you can learn with it. Thank you.